Suppose you're looking for a job, and a friend tells you about a training program where 80% of attendees landed high-income positions. Should you enroll? Being an avid watcher of this channel, you know that this doesn't tell you that the program caused enrollees to get high-income positions. It could be that more motivated people were both more likely to enroll and more likely to get a job come what may. So you can't learn the effect from the observed probabilities. But let's say the program was tested in a rigorous study, in which a large population was randomly assigned to enroll or not enroll in the program. Such a study could in fact tell you that the program was causally effective. So, should you go for it? After a bit of thought, more doubts surface. What does the study population have to do with your population? Maybe the study was done in California, and you live in the Midwest. Or maybe it was done 10 years ago, in a very different labor market. In other words, even if the study was done perfectly, there's no guarantee that its findings will generalize to other populations. This is called the problem of causal extrapolation, and is the topic of today's episode. Hello, and welcome to Causal Foundations. I'm Naftali Weinberger, a philosopher of science who's been researching causal models for over a decade. In this series, I introduce foundational concepts from causal inference in videos of approximately 10 minutes. In our example, the effect identified is an average effect. To illustrate, suppose that motivated individuals gain more skills from the program, increasing their chances of getting a high-income position by 20%, while for those less motivated, the increase was 10%. The average effect would just be the average of the effect in each group, weighted by their sizes. So if there were as many motivated and less motivated people, the average effect would be 15%. Crucially, you can identify this effect without knowing how many people are in the motivated and unmotivated populations. The effect implicitly averages over all background factors in the population. But now suppose we wanted to extrapolate from a study population to a population with a different proportion of motivated individuals. How should we formalize this problem? One option is to suppose that we hadn't identified the effects for the motivated and unmotivated subpopulations in the study. Since we're assuming that the target population differs in the distribution of motivated individuals, and we don't know how this influences the average effect, clearly we don't know the effect in the target population. So let's imagine that we did measure the subpopulation effects for the study population. Now extrapolation is simple. We can derive the effect in the target population by reweighting for the proportion of motivated and unmotivated individuals. In other words, since we've already identified the effect for both the motivated and unmotivated subpopulations in the study, and we've stipulated that the target population only differs in terms of the distribution of the motivated, the effect in the target is just a reweighted sum of the subpopulation effects. So it seems like depending how we characterize the problem, extrapolation either seems unsolvable or trivially solved. In order to characterize the problem of extrapolation, we need a way of representing that the study and target populations differ without specifying precisely what accounts for the difference. Yuda Pearl and Elias Bareinboim's Transportability framework allows you to do just this. This framework enables you to combine the graphs for the study and target populations into a single graph, and to indicate the points at which the populations differ using something called an S-node. Here the S-node into motivation indicates that the populations differ in the mechanism determining the probability of motivation, and the absence of S-nodes into X and Y indicates that those variables' mechanisms remain the same across populations. Transportability is employed in contexts in which at least some of the causal relationships are confounded by omitted common causes. In the study population, we assume that one can intervene on any variable to identify all the causal relationships. For the target population, we know the observational probability distribution, but cannot intervene. The probability distribution for the target population corresponds to the result of taking the distribution for the study population and conditioning on S. Transportability concerns whether one can combine the information learned from the study population with one's observations of the target population in order to identify the effect in the target population without intervening. Now that I've given an overview of transportability, let's apply it to some simple cases. First, suppose that X causes Y, and that there's an S node into X. Here the effect does transport, since it doesn't vary across the populations. Once one identifies the effect by intervening on the study population, it carries directly over to the target. Now imagine that the S node goes into Y. Here the effect is not transportable, since it can be arbitrarily different in the target, and we can't learn it without intervening. We're now ready to consider a more interesting case. Let's return to our example of the effect of a jobs program on getting a high-income position. Presumably this effect is confounded, and we expect it to differ across populations. So in this model, the effect is not transportable. But perhaps we know more about how the cause produces its effect. Plausibly, one way that the program influences employment is via teaching skills. If we were considering two populations where the main difference was in whether they acquired skills as part of the program, then the S node would go into skills rather than the outcome. And in this model, the effect is transportable. The basic idea is that since we already know the effect of X and M on Y from the study population, and can observationally identify the effect of X on M in the target population, these effects can be combined. Let's see how this works. Here I'll be relying on concepts covered in episodes 2 to 5. But even if you haven't seen those, the following should give you a sense of how transportability can be applied. We're trying to learn the effect of X and Y in the target population, where the target distribution is just the study distribution conditional on S. We can take this distribution and marginalize out M as follows. The probability of Y given do X and S is equal to the sum over M of the probability of Y given do X, S and M times the probability of M given do X and S. While this looks complicated, it's just a standard application of probability theory. Consider the first term. Note that conditional on X in the causal graph, MD separates S from Y. More specifically, M blocks the transmission of influence from S to Y, while opening up an additional path, which in turn is blocked by X. Because MD separates S from Y conditional on X, we can remove S from the first term. Now consider the second term. The effect of M given do X and S just is the effect of X on M in the target population. And since X and M have no common causes, this effect is identified without intervening. So we can transport the first term from the study and identify the second from the target. By combining them, we get the effect of X and Y in the target population. Transportability addresses a particular type of extrapolation problem. It relies on the assumption that at least some variables in a DAG lack S nodes, so we can transfer causal mechanisms across populations. So should we say that extrapolation just is transportability, and that the problem is now formally solved? I'd argue no. Recall that the problem was initially formulated in terms of populations. Will a cause discovered in one population be similarly strong in another? But the term population is not a technical term in causal inference. Instead, DAGs apply to probability distributions over sets of variables, and it's non-trivial to determine which probability distribution best characterizes a particular population. That's why we need statistics. So there are as many versions of extrapolation as there are ways of characterizing the populations, and this means that the problem can be addressed with many toolkits. Thank you for listening. If you've made it this far, please don't forget to like and subscribe.